Hello student, welcome to today's session. So today we will be discussing some important questions in regard to the organic chemistry. So these are some challenging questions which could be very important for upcoming JEE Mains Advanced and NEET examinations. So in these questions, the examiner is going to check how good you are in the understanding of organic chemistry in terms of the conceptual aspect as well as from the viewpoint of how much you are knowing about the reagents which are being added in the reaction sequence. What is the role of those reagent and how they are going to give the products? So here comes the first question. That here in this question you are supposed to identify the incorrect statement for the following sequence of reaction. So question seems like very interesting, where lot many things would be checked. Now let us check this out, what is being said about it. So the starting material is being treated with the H positive, and then there is a role of zinc, KMnO4, heating, phenol, and sulfuric acid. So these are the reagents which you are supposed to add one by one. First, you have to start with the first reagent. Now, in the first case, when you talk about the starting material, and this is to be treated with H positive, as I told you many number of times that whenever any starting material is being treated with H positive, before you give the final product you have to deprotonate it. So let's check this out. And one way is that there is a lone pair availability. So the lone pair would be attacked by the H positive because H positive is looking for electrons, and then you end up getting this sort of a species. One thought process can be this way. So this is having a positive charge. Now, this particular species may undergo resonance of the type this way, and as a consequence, you end up getting a carbocation of this nature, which may be said as to be secondary carbocation. Other way around, someone else can also think it this way, that why we have not attacked the pi bond. Say, for example, if you would have attacked the pi bond, then the carbocation which I am going to obtain here in this case would not be very stable, because the carbonyl group is a strong electron withdrawing group. It is going to destabilize the carbocation. So this is the electron withdrawing group. Or someone else can attack onto this side of the H positive, this side of the pi bond. In that case, the carbocation would be rather more unstable because the positive charge went close to the carbonyl group. So this is highly unstable. So to begin with, it seems like that the reaction would go from this direction. So we have reached to a point that we generated a carbocation. Now you have to do the deprotonation. Let me do it in a speedier way once again. So the lone pair attack this, and you end up getting this species is being generated, and then this species is quite stable because the octet of all the elements is complete compared to the other carbocation in the previous slide. Now this underwent resonance, and during this resonance, what did you get with? So you ended up getting a entity like this. Now we wanted to do the deprotonation. So deprotonation has to happen from a carbon next to the C positive. So the next to the C positive either is this hydrogen, which would not undergo deprotonation because it is sp2 hybridized, as well as if I do the deprotonation from here, you would get a double bond here. So in a cyclic structure onto the same carbon, if two double bonds are there, that would not be stable because it would try to become a linear, but it would not become linear. The other option which I am left with is that there is CH3, CH3. So if in case I do the methyl shift here, so then what shall then I be getting? So I shall be getting something of this nature. So I did the methyl shift. Now once I did the methyl shift, now you have to visualize that where the positive charge has gone to. So you brought these two electrons. If you carefully see, these two electrons came along with CH3, and as a consequence this would get a positive charge. This got a positive charge. Now I don't know how many of you have seen that in this particular question you need to be little vigilant about the hydrogens. So here you have one hydrogen, which I don't know whether you have noticed it or not. Now this hydrogen now could undergo deprotonation. So beautiful question it is, and this lead to a benzoid type of a structure, and you end up getting a species of this type. This is a sort of phenol, substituted phenol, where if I would mark it like this, 1, 2, 3, 4, 5, 6. So it is 3,4 dimethyl phenol. 3,4 dimethyl phenol type of a species is being generated. Okay, so this is one way of the thought process. So I don't know how many of you have understood it or not, but the point here is that first in this case we have generated a phenolic group here. So a phenolic group is generated along with the two methyl groups onto the substitution. So in a way, it's an interesting one. Now it is to be treated with zinc. Now what is the role being played by zinc dust? So zinc dust is being used to do the removal of oxygen from the phenol. So if you heat it with zinc dust, this zinc oxide would go out and you end up getting benzene. You end up getting benzene. So basically zinc went from 0 to +2 oxidation state, 0 to +2 oxidation state. So in that process, zinc underwent oxidation and phenols reduction has happened. So this is one thing which you should know about. So our starting material had been this one. So if you have this one with you, zinc heating, and you would get a species which may now be said as orthoxylene. Common name of this is orthoxylene, or you can say 1,2-dimethylbenzene. So we end up getting 1,2-dimethylbenzene. So here we have to see it once again that where we reached. So this is what we reached. So on treatment with zinc, what we end up getting here is OH went out and we got a xylene. This xylene is created. And this xylene is to be treated with KMnO4, which is a strong oxidizing agent. And I know for sure you must be knowing that what is the role being played by KMnO4. So wherever a KMnO4 is treated with a hydrocarbon of the type where a hydrocarbon chain is attached to the benzene. Now here I should mark it very categorical statement that whenever you have any benzylic hydrogen, if a compound is having benzylic hydrogen atoms are the hydrogen attached to carbon next to benzene, or uh, next to the benzene carbon, if there is one hydrogen and it is being treated with KMnO4, then this carbon, which must should have one at least one hydrogen, benzylic hydrogen is must, one or more benzylic hydrogen are required. If you do so, the oxidation of KMnO4 would result in carboxylic acid. You would get carboxylic acid. Just like in this case, if I do so, the KMnO4 oxidation would convert this into COH, and the other hydrogens would go out as water. This is quite an important one. So you need to have hydrogen. You need to have benzylic hydrogen at least one. So if in case I just would treat it with KMnO4, as I just have said, you end up getting benzoic acid, and same answer you may also get with ethyl benzene also. If you are being treated, if you are treating it with ethyl benzene, KMnO4, and along with heating, you would get this benzoic acid from here also, because this carbon is still having two hydrogen atoms, and rest of the carbon would go out as carbon dioxide and water. Whatever is the requirement of the oxygen, that KMnO4 keep on fulfilling it. And similarly, if you have isopropyl benzene, this is isopropyl benzene, which is popularly called as cumene. This is a very common name of this compound, cumene. This also would give you benzoic acid when treated with KMnO4, because it still have one hydrogen attached, benzylic hydrogen to the carbon, and rest of the carbons would go out as carbon dioxide and water. Whatever is the requirement of oxygen, that would be fulfilled by KMnO4. But if you have a tertiary butyl benzene, just like in this case, if you have a tertiary butyl benzene, here you would not be having no benzylic hydrogen. There is no benzylic hydrogen atoms. So if there is no benzylic hydrogen atoms, the KMnO4 reaction would not so there we would see that there would be no reaction taking place here. There would be no reaction taking place. So in the one question, discussion of one question is bringing in lot many things into the discussion. So just like if we started with in this one, we ended up getting one of the product at the last slide as orthoxylene. Orthoxylene, when treated with KMnO4 in the presence of H positive, so there are benzylic hydrogen here, benzylic hydrogen here. So this would convert into dicarboxylic acid, which we commonly say it as to be phthalic acid. So you are going to get phthalic acid as one of the product in the reaction sequence. So where we have reached. So this B shall then be phthalic acid. This is phthalic acid. This would give you phthalic acid because both of these CH3 got converted into COOH group. Now this is to be heated, and any dicarboxylic acid of the type 1,4-dioic acid when heated simply would undergo dehydration. This would undergo dehydration to give you what is a popular compound which we call it as phthalic anhydride. This we get with one of the products. So this is, we say it as to be phthalic anhydride. So good question it is. It is checking lot many things, and to be done in 3-4 minutes. Such questions would require good amount of understanding as well as speed, and this would come only if you have done good amount of practice. And the last step, which is again a very interesting one, because here what we have received, we just have said that we got phthalic anhydride. We got phthalic anhydride at this stage. Now, phthalic anhydride, phenol and sulfuric acid, if you could recall, this would lead to the formation of a very important acid-base acid-base indicator, which we call it as phenolphthalein, if you could remember. So here you can directly write an answer if you know the information from the understanding of +2 organic chemistry, that phenol, phthalic anhydride in the presence of sulfuric acid gives you phenolphthalein directly. So if in case you are not recalling, you can remember it like this. Somewhere later on, we will be discussing the mechanistic viewpoint of this one also. If you have this phenol, just treated with concentrated sulfuric acid, and here I'm just writing the shortcut. So this compound which we receive here, this particular compound is said as to be phenolphthalein. This do engage a good amount of understanding of the mechanism, but at this point of time, let's first solve the problem, and some in other lecture I will explain it about the mechanistic viewpoint about this particular reaction. So water goes out, and this particular compound we call it as phenolphthalein. So in the one question, lot many things have been checked. So the last answer we got is the phenolphthalein. Now we need to check what the options given to us. B is phthalic acid. Yes, it was phthalic acid. I think, yeah, it is phthalic acid. So this statement in itself is a right one. D is phenolphthalein. This also is correct. A is a substituted phenol. This in a way also is correct. And C is succinic hydride. This is wrong. Succinic hydride is this entity. It comes from the succinic acid. 1,4-dioic acid, when underwent dehydration, when this underwent dehydration, it would lead to form the, so the water goes out from here. This is succinic acid, 1,4-dioic acid, and this gives you succinic anhydride. Succinic anhydride has never been found in this particular reaction. In fact, it resulted in the formation of phthalic anhydride. The anhydride which we received is the phthalic anhydride. So C would be a wrong option. It's a wrong option, but is a correct answer for this particular question. I hope you have understood this particular question. Now let's do one more question on to this topic only, and let me write one statement for this particular compound. You always have to remember that if you just like in the first reaction, first step of the reaction was very important because it resulted in the formation of a aromatic character along with the formation of phenol, and you end up getting this type of a compound. So this in a way is also said as diene, because there are two double bonds. If you could see diene, and one means a keto group is also there, and and what you basically have generated here is a phenolic group. So this also is commonly said as diene-phenol rearrangement. So what is the rule of the game? When you have a diene of the type, just like this, if I would draw it once again, if you have diene-on, this type of a species is with you, just like this one, it is being treated with H positive. This would undergo rearrangement to give you a phenol type of a structure. This always you always have to remember with. Now coming on to the next question. Next question also is a quite an interesting one, although it seems like a easier one, just like the one we just have finished with. It seems like on to the same pedagogy, same philosophy should be applied in this particular case also. Again, you could categorically see that the species which we have got is a diene diol. This is diene on, and you are creating a phenolic group. So it is somewhat in the same context as we did in the previous question. But is it the same way or is it something else to do with? So the question is beautiful. I find this question to be very interesting. Let's check this out, what exactly is being asked in this particular question. So let's read the question first. In the following reaction sequence, on which position second methyl would attach in the final product if reaction involved both ring contraction and expansion during the mechanism? Now here you need to understand, in the organic chemistry you have to read the mind of the examiner, because there are a lot many parallel reactions going on, but in which direction examiner is wanting us to go for. Now let's check this out, because here you have two methyl groups. In the final product I just would see one methyl group. So he is asking that where the second methyl get attached with, and he have marked the numbers also. Would it be on 2, 3, 10, 5, 6, 7, 8, 9, where it is going to attach with? Now let's do this question and see what can be the solution for this question. So here I would not be attacking onto the I shall not be attacking onto the double bond, because we just have said that it is diene on phenol rearrangement where the H positive has to attack onto the lone pair. So the H positive attacks onto this lone pair. Now let's see what next structure. This we have to do it very cautiously, because I think the questions, the way the question is being represented seems like easy, but it is not so easy. Because why is it not easy? Because if I just would want to do the deprotonation, I am not seeing any hydrogen available, because here you have a methyl, here you have a methyl. I could see one hydrogen here and one hydrogen here. Nowhere else I just would see the hydrogens. I could see hydrogen here also. Of course, there are two hydrogens here on to the other side of the, but as per the options, as per the answer, because at the final stage I just would want to create a phenolic group, aromatic character I just would want. So there is nothing would come from this direction. So I can simply could rule out a few options out of, okay, let me do first and then we'll see the discussion. Okay, so here what next I could see here is either I can bring it this way. One style could be this way. This is nothing but resonating structure. Or the other way around, you can go it like this also. Is it okay? So let us do the both ways. If I go with the red direction, the way I have shown with the red marker, so here you have methyl, methyl, and this now would become OH. And here you got, if you go with the red marker, I'm saying, if you are going with the red marker, this bond goes here, this goes here, and the positive charge would come here. One style can be this way. So if I went with the red, and if I just would go with the green, these are nothing but resonating structure as a matter of fact. So here you would get with something of this type. So the methyl is here, and this bond goes here, and you would get OH. Yes, and this one, and here you would get a positive charge here. So both of these are nothing but resonating structure. As a matter of fact, you can go here and go here, you get back the same thing. So these are nothing but resonating structure itself. Am I right? Now the point here is that once you have achieved the structure, now let me show you what the problem we are stuck with. So you happen to receive this one. Here you have, this is the OH we got and the positive charge on this direction, and we are here somewhere. Or the other way around, if you just would take its resonating structure, we need to do it little patiently. Otherwise, we end up getting a wrong conclusion. So, or the positive charge could be here. Now, the problem I am seeing myself stuck with is that I do not have H positive for the deprotonation. H positive cannot deproton, although there is a hydrogen here, but this H positive would not deprotonate because onto the same carbon, if you would get two double bonds on both sides, it would try to become linear, it would not be stable. So, and also it would not result in a aromatic character. Now, okay, other thing you can think of this way, this hydrogen can be deprotonated, and this fairly can undergo deprotonation, because if I would create a double bond here, this is in conjugation as well, but it would not lead to aromatic character. So here's the problem. And what about this one? Same situation is here. If you deprotonate this two pi bonds would come onto the same carbon in a cyclic structure, which would not be stable, which because it would want to become linear and it would not create a aromatic character. And here I don't have any hydrogen because this is methyl. This is methyl. And as a matter of fact, if in case I do a sort of methyl shift also, after the methyl shift also, I would not be getting the available hydrogen to make the thing aromatic, isn't it? If I just would do the uh, this is not the right approach, but let's go for it. So if I just would do, so there is methyl here, there is methyl here, so I cannot get the deprotonation again done with. So I am somewhere stuck with, and that is where the examiner is guiding us to go for the direction which would involve a sort of ring contraction, ring expansion. Let's check this out little more carefully. So where we are somewhere here, we stuck somewhere here, and this is the way organic. So if in case you also get stuck in such type of a situation while practicing organic questions or during the exam, do it little patiently. If you do it patiently, something somewhere would click you. Now, just like if I just do it this way, that I just would do the ring contraction, because there is a thing which is being suggested by the examiner. So if I do the ring contraction, what then? Let's check this out. If I could get something out of it. So if I do the ring contraction of this type, so where I should reach to. So let me mark this as numbers also. So this is, if I would go from this 1, 2, 3, 4, 5, and this is 6. So what we did a somewhat like this. So this goes here, something of this type we have done. So if I just would mark these numbers, 1, this is 2, this is 3, this is 4, this is 5, and this one is 6, which is also containing one methyl, and now it do get a positive charge also, isn't it? It would get a positive charge. 6 would get a positive charge. Why would 6 get a positive charge? Because this green electron which I just have marked is of the 6th carbon, and the cross is of the 5th, and 5th is still retaining the cross, and dot goes to the first carbon. So as a result, 6th carbon get a positive charge. Now, would it help us to do some sort of deprotonation? Still not, but I am able to see something very beautiful coming from here. So if I just would do the resonance once again this way, this is nothing but a resonating structure I created. So this resonating structure would make the species of this type. Just do it carefully. You would get double bond here, and this was the OH, and here you get a positive charge. Here you get a positive charge, and along with it, you have a 5-membered ring. 5-membered ring. Now, many of you would start getting the approach. you start feeling what sir is going to do now. Now what I can do here is that I just would open up this one. If I would open up this one, because the fact of the matter is here I am able to see one hydrogen. There is still one hydrogen lying here. Here is one hydrogen available. Let me mark it once more for you. I just have said that there is one, there is one hydrogen available. There is one hydrogen available and it is carrying, here you have a positive charge. Now, if I would bring it here, what next structure do I get here? The next structure I do get here is something of this nature. Let me mark it. Here you would get OH, and this is the same way. And if I just again would mark 1, 2, 3, 4, 5, and this is the sixth carbon. So fifth and sixth got joined. So this I could see like this. So if I just would mark it, what was this? This was the first, second, third, fourth, fifth, and the sixth. And the electron of 1, this is the electron of 1 which went to the 6, dot and cross. Cross is of the 5, and 5 is still retaining the cross, and sixth carbon now would accept the dot of the first carbon. In a way, it would generate a positive charge onto the first carbon. So carbocation is generated at the first carbon. So let me mark it with another color. So you get a positive charge. And now you could see I was having here hydrogen, which is of the type of sp3, which can easily undergo deprotonation. Now, if this deprotonation has happened, so this you would get a double bond here. Now, once you get a double bond here, what next you can think about? So let me, although the things have become little chaotic, but let me show you here only. So thereafter, otherwise I have to make it once again for you. Array. So here it goes, the product formation is of this type. So beautiful question it had been. And here you have a methyl, and this was OH, and here you would get a double bond created here. Now what you are able to see here is that this compound is being generated. Let me write it once again for you. We got this product, and this is the product which is there shown in the option, also shown in the starting question also as a product. So what we are able to see here is, if I just would mark it from here, so this is 1, 2, 3, 4, 5, 6, something like this. Now we have to really go by the fact that how the marking is being shown in the problem, because I cannot use my style of numbering. So here is some numbering given to you. So we are able to see that we generated this product. Now we have to match our answer with this options, isn't it? So this is what they have shown, and here you have a methyl. So I could see very categorically that one of the methyl, they already have gave us this methyl and this OH are para to each other. Okay, fair enough. So this means the next methyl would get its position adjacent to the methyl group. So here somewhere here I would get a methyl. Am I right? I'm perfectly right. So this is the way it is to be approached with, because they already have marked 1, 2, 3, 4. So that means the position it is going to acquire, the second methyl is going to acquire a position in the final product at the third position. So this would be the C answer for this particular question. Wow question. It is a beautiful question. I hope you enjoyed it. So you need to do the questions with, so it is just like mathematics, more you practice, more you learn. So I'm leaving you with one homework question. So this is a homework question. I just would see how many of you could attempt it and how many of you would get with the right answer. So in this question, what the single integer type question, what is the degree of unsaturation in the final product of, the final product is aromatic, and you now have to develop the mechanistic viewpoint. Again, this is a dienone type of a species which is being attacked by H positive, and then you have to do sequence of reaction. Here NBS means N-bromosuccinamide. Now you have to brush your uh, memory that what basically is the role being done by NBS, N-bromosuccinamide. So hope to see you in the next session, and do answer it onto the comments section if in case you get the answer. And next time, somewhere in the next video, I'm going to explain this problem once again. Bye bye, take care, have a nice day, stay safe.